Hey everyone, welcome back to the channel. This is the first video of this playlist, and in this video we're going to discuss about miscellaneous topics of atomic structure. So today we'll start with the history of atomic structure and how it is originating and what it is originating from. So let's start with the planetary model of atomic structure. So the planetary model states that there is a nucleus, a center, and we have electrons just orbiting somewhere around nucleus. This electron. So this is the model. But there's a problem with this. According to electromagnetic theory, we know that if a charged body is rotating around nucleus, then it needs to radiate energy, needs to give out some energy, and then spiral down into nucleus. But in reality, that is not happening. So, this model doesn't really tell how electron is staying in its own orbit and not collapsing into nucleus. So, there's something wrong with this model. So, that's one part of history. And then came de Broglie. So, de Broglie told that electron is a wave. Okay, so electrons are wave. How is it? And why is it a wave? The questions. So if it's a wave, would it have an equation? It would. That is called wave equation. And another question is, how exactly is this electron physically there? So we don't know how it actually exists. And third one is, when you're saying electrons are wave, what exactly is waving? What is waving in an electron? So we need to answer some of these questions. So this model failed, and we found that electrons is not just a particle, but it's a wave. So do you have any questions? Yes. How is it physically? We don't know. What is waving? We don't know. So this is a piece of history, and then came Schrodinger. So Schrodinger gave an answer to this wave equation. He found an equation, a formula to describe and calculate the wave equation. But he tried to maybe try kind of answering this, how this electron exists physically to an extent, and he told that this is the wave equation that he found out, and he told that the peaks where the equation is high, he said that the charge is high, that is, electron charge is high at this particular point, and here, and here. So his explanation is that electron doesn't exist at one point somewhere, but is spread out. So electron charge is spread out through the atom, and we'll find different places where charge is high. But then this model is debunked later and proved that it is false. So here is another model again. So there came another scientist, Max Born. So Born suggested that the wave equation psi doesn't hold any information, but psi square holds every information that is needed. So what does the psi square actually hold? He told that psi square is the probability of finding an electron. Wow, what do you mean by probability of finding an electron? So the psi square will be a function of position x, y, z and times. So if you can substitute our coordinates and time at which we want it, we will get the probability of it existing at that particular time and this particular position. We get that probability. So, but we still didn't answer the other questions. So, another experiment is carried out, stating that when we heat up hydrogen atom and then we see the spectrum of it, spectrum in the sense the energies that are released by this hydrogen atom after heating up, when we put it in a spectrum, we got only particular ranges of frequencies where the energy existed. So this is the frequency, this is the energy. So this energy only existed at particular frequencies, but other frequencies is just zero. But that's the problem. Why are there discrete energies only at certain frequencies? We don't know that. That's one question. Discrete energies. Okay, so a lot of questions, and we need to find the answers to them. So let's just try to answer these questions. Maybe we'll start with answering this. So before going into that, we need to know that our electron is a wave. So what exactly is waving? Let's just say, as in light. Let's see the double slit experiment wherein you have two slits and this is a detector and we send light in two slits and then there will be light, sorry, interference and we'll see maxima and some minima somewhere. So there will be constructive and destructive interferences, right? Similarly, instead of light, we assume an electron sent between two slits. Then what happens is the probabilities of psi of both will do constructive and destructive interferences and forms maximus and minimus similar to light. So what does this maxima and minima interferences signify? So maxima signifies that both electron wave functions had constructive interference and the probability of finding an electron is higher at these points, whereas at these points it is lower because the psi of this and psi of other electron had destructive interferences. So this is what we meant by the equation and this is what we meant as in wave. So now, now that we know what exactly is wave nature in this electron, let's proceed to something other. Uh, the previous question of discrete energies. How do you know that it is discrete energy? Why we are getting discrete energies? So, hmm, if our electron exists around nucleus somewhere, what kind of wave would it be? We don't know that, but let's assume a standing wave. And standing wave, a stationary wave, we'll assume stationary wave, it is held between 2 points and it can wave in different ways, but they are all they all have integral multiple frequencies. So multiple frequencies. So yeah, this is 0, 1, 2, 3. So yeah, these are the standing waves or stationary waves confining. So this is a good example of how an electron wave is, because if you say an electron exists here, then it is bound by 2 points. One is nucleus. So this is one point, and the other point is somewhere at infinity. But so these are the 2 points between which electron can have a wave function, right? So let's assume it can wave like this. This is the minimal energy that an electron can take. It can have a uniform distribution, right? Or yeah, this is the minimal electron wave function can be. So when we go down this way, the energy is increasing, the frequency is increasing, so your energy is increasing. So this is the minimal energy that an electron can have. So let's just map this to our model. So, so this is our psi. Then what will be our psi square? Psi square will be square of psi. So this will be a psi square. It's confined between 2 points. One will be a nucleus, another will be a infinite. So this is our nucleus. So then psi square represents the probability of finding an electron. So it peaks at some particular point and then goes down. So we should assume a 3D model of nucleus, and you can safely say that the probability of finding an electron peaks at some region very much, but it's not very much likely to exist here or here. It just peaks around particular area, particular region. So this is the basic minimal energy that an electron can take, and this is called s orbital, and it's 1s because it's the minimal energy it can take, and this is considered 1. So now, similarly, let's map this onto the next standing wave possible, and that is this. This is the second. So this is the psi. Then psi square is going to be in the same shape almost. except that it is the square of it. So psi square, right? Okay. So yeah, we have a node here. See? So this is where your psi square is zero. So let's just map into our model nucleus. We have two peaks. Let's just draw the two peaks. One, two. So these are the two peaks, and have a node in between. So this is our two peaks. Sorry, my mistake. It's actually top, not bottom. So we have a node in between. So you won't find any electron in this region. This region in between is just going to be empty, and the probability of finding an electron at the point or at the shell is actually zero. So you have a peaking probability here, and then it goes to zero, and then it goes high, and then it goes to zero. So this is called 2s. Okay. Now this is another thing. We assume one node in our standing wave. Similarly, we assume one node which is spherical in shape. Instead of assuming a node spherical in shape, we can assume a plane node, which is a spherical node. Instead, if we assume a plane node, which is passing in between, and this node needs to be symmetric, since both are symmetric in nature. See? So our node in between needs to be symmetric. So in 2D space, a node is going to be just only a line, but in 3D, it needs to be a plane. Let's assume this is our nucleus, and our plane goes right through nucleus, so it looks like this. Then, along with that, we have two peaks along with it, so we'll, we'll have the probability of finding an electron high between two areas, and then here too. So yeah, this is called p orbital. This doesn't look like a textbook p orbital, but it kind of translates something similar like this, right? You have a node somewhere here, and your other p is down here. So this is your p orbital. And remember, your node can go this way too, and the other way, diagonals and other directions. So that raises p, x, and y and z orbitals, second order, right? Similarly, we can just go on to 3, 4, and so on. But let's just see the 3d orbital ones. So, how does this originate? This, okay, before this, I need to tell you that. So, a second order one gave one node, and this 3D will give rise to two nodes. So, you need to arrange two nodes in the atomic structure. So, two nodes can be radial, or could be angular, radial, could be angular, right? So, so it's not about the just n equal to 3, we have two nodes, and two radials will give rise to s orbital, namely the third one. This gives rise to p, and this gives rise to 3d, right? So we know how these two orbitals exist and how to derive. So let's just look at this 3D. So this is the nucleus. So this d orbital will have two angular nodes. So the two angular nodes could be like this. Two planes perpendicular, since it needs to be symmetric, so they're perpendicular, and that's it. Your electron can exist here, it can exist here, it can exist here, it can exist here, right? So yeah, this, 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 this. So it looks like a D outer, right? Which is in textbooks. Similarly, these two planes can be arranged in different directions and everything, and it gives rise to multiple d orbitals, the X, Y, the YZ, the ZX, and so on and so forth. So this is how the orbitals are originated. So then let's see how we name an electron. So an electron can be distinguished with its particular frequency in which it is responding, right? It could be in any one of these spanning wave configurations. So we named 1, 2, 3 previously. So this is called N. So this N describes a part of electron state. And next quantum number that defines an electron is called L. And what does this L describe is the number of angular nodes. We've seen in this case that there can be one angular node when n equal to 2. And similarly, when n equal to 1, there can be 0 angular nodes. And when n equal to 3, there can be one angular node or two angular nodes. So from this, we can say that L can be from 0 to so on till n minus 1, right? So this defines L, this is called azimuthal quantum number, and then comes M. M describes the way in which these nodes can be arranged, right? The way nodes are arranged could be radial and angular, angular. So everything is distinguished by its particular M. And M generally takes up values from minus L to L. So n L equal to, so say n equal to 3 or 2, then L is 1. Then n is minus 1 or 0 or 1. And this NLM define an orbital. These things can define an orbital. Now, to define an electron inside an orbital can have two electrons, right? But for real symmetry purposes, these two need to be aligned in different directions. So that uh, gave rise to a new quantum number called S. And spin quantum number can be half or minus half. So an electron in an atom will have its own distinct N, L, and N as quantum numbers, right? So yeah,